All right, now you're going to have to get your thinking going here, because I'm going to take everything that we've known, right? We're going to obviously take it a step farther, and we are going to start considering, when you mix things together, okay, now we can say, will a reaction occur or not? In other words, will I see a precipitate form or whatever? We've talked about that already. You can look at that chart and see what happens. You know how to name things. You know how to write chemical equations for things. Now we're going to take it a step farther and look and see, in chemical reactions, keep track of our quantities, how much we have of a certain reactant. And if we know how much of this reactant we have and how much of this reactant we have, how much actual product can form. We're starting to answer some pretty important questions now. This applies all the way to biology and the chemical equations that go inside of happen inside of our body, the energy extractions that we perform, or whether it's industrial chemistry, trying to make stuff out there that we use every day. These are very, very important questions that people have to be answered. What is the input compared to the output of this? Is it an energy efficient process? Do I need a whole lot of something? Am I going to have to waste something? What is going to be what's called my limiting reactant? What amount is going to drive how much product I'm going to make? Okay, so those are the kind of questions we're going to answer with this. All right. So everything is related. The reason that chemical equations are so important now is because, number one, it gives you an idea of just what's happening, the formula of the things involved, but also you have to balance it. And by balancing it, what it tells us is the recipe for this chemical equation. It tells you the different, if you have a recipe and you've got a cup of sugar and 3 cups of whatever, you got to realize that that's very specific to your particular recipe. If you start changing that, it may not taste like you want it to. Okay? The same thing is with chemical reactions. There's a certain recipe that has to exist for these things to occur. And if you don't balance your equation right, you've got the wrong recipe and you won't be able to answer any questions correctly concerning it. So, if you know the balanced equation, what you have is a relative relationship of all the things involved. How much of each, basically, is going to be involved. Okay? All right. Now, what we're getting ready to study, okay, what this last bullet says is the study of the numerical relationship between chemical quantities in a chemical reaction. In other words, how the numbers of everything in a chemical reaction relate to one another. We call this stoichiometry. Okay? Another word for the day. Stoichiometry. It's a big word. I think you can grasp the concept, though, as we go through here. So if I say this, you'll know what I'm talking about. It's using chemical equations, using the numbers in chemical equations, like the 1 or the 3 NaOH or the 4 HCl or whatever. Using those numbers to answer questions, basically, is what stoichiometry is. Okay, for example, not to get on a soapbox or anything, but I'll show you how we can answer this question here in a second. Let's talk about global warming. Right, it doesn't exist, right? It's all just a big made-up thing. Anyways, without getting into the ethics involved or the problems or whatever, just how do we get this data? Because some people might say, and people like you and every other person out there, or even if you want to do it this way, how do we know that, or not that we know, but how do we guess that the world is, say, 4 to 5 billion years old? And the universe is 15 billion years old. Where do these numbers even come from, since there's no way that people have been here for 15 billion years? None of us here, anyways, who are measuring this crap could ever come up with 15 billion years. So how do we get it, and how do scientists subscribe to the fact that that is valid data? These are some of the answers that we're going to see. For example, we have noticed that there's an average of a 0.6 degrees Celsius rise in the atmospheric temperature since 1860. Now, that doesn't seem like much to you, maybe. But what you've got to realize is that 0.6 degrees rise in temperature is not just right here in Terre Haute. That 0.6 degrees rise is all over the world, on average, wherever they have temperature probes set. And a 0.6 degrees could be the difference very easily between something melting and something staying solid. So obviously the bigger impact is going to be a little farther north, a little farther south, when you start getting into polar regions. And also realize that once things start melting and pressure starts changing in the atmosphere, wind patterns start changing, currents and jet streams start changing, weather starts changing. Not to be drastic, but of course you've probably seen like the day after tomorrow and all that kind of stuff. And that's way out there. Theoretically possible, I suppose, but I'm not saying that I'm not going to stand up with a little sign and picket on the side of the road telling you it's Armageddon's upon us and all this or anything, but realize that there is an issue here that we should be concerned with and at least explore just in case it really is what it says it is. There has been, according to the data, from about 1860, you can see the average temperatures have been climbing over the past, 140 years or so. It's very interesting, though. Anybody know what was going on in the world around the 1860s or so? There's an era of time that we call the what? Whoa, no, not the Ice Age. The Industrial Revolution. Okay, about the time we started putting up a bunch of factories and consuming a lot of fossil fuels and doing all this stuff, and industry starts to boom. This is about the time we start seeing these trends. Okay, so that's interesting to point out. So also, just to give you an idea of how long ago this was, Civil War days, right? 61 to 65 is the Civil War, 1860. So right around that time. Also over in Austria, and about this time, there was a guy named Gregor Mendel who was working with pea plants who came up with all the rules of Mendelian genetics, right? All right. Anyways, the way this works is, of course, increased production of carbon dioxide, right, into the atmosphere that basically acts like a blanket. So when these sunlight rays, whenever they start coming in here, these greenhouse gases, especially carbon dioxide, there's some other gases up there, actually act like a blanket and trap this in. Okay, that's the easy way to explain it. But here's what's interesting. How do we know? How do we measure this? We can measure temperature, but how do we know that CO2 is the culprit? How do we know all of this stuff? Well, what we have noticed at the same time is during the same period, atmospheric CO2 levels have risen by 25%. Now, 25%, 0.6 degrees may seem like a big difference, but we're well on our way to just exponentially increasing our CO2 output as a world culture. Okay, so the CO2 levels have risen. So is there a correlation? It's certainly worth checking out, because if we note that, okay, this really didn't, we see a visible trend. We don't know what happened in the past. It could be that these same temperature spikes happened, many, many years ago, maybe during the dinosaurs, maybe other times. I mean, we weren't around. We didn't have instrumentation to collect that kind of data. We're not saying that it's impossible that this isn't a natural cycle. Maybe it very well is. But what's interesting is it does correspond directly to the Industrial Revolution. And also, given this same amount of time, we have seen a 25% rise in atmospheric carbon dioxide. Now, take that for what it's worth. Maybe you think, coincidence, bunch of crap, sweep it under the rug, forget about it, let's keep driving our SUVs. And that's fine, maybe. You have that right. But realize there's something that would pose a question. There's something that's interesting about this that deserves further exploration. Are the two trends causal? Are they related? Does one cause the other? Well, how would you come up with this kind of data? Because imagine how hard it would be to measure all of the carbon dioxide production that's in the world, like from automobiles. It doesn't seem very feasible. You can't strap on some kind of device to all of the exhaust systems of every single person's automobile on the entire planet. So what do you do? How can you come up with a number that supports how much we are putting in the atmosphere just from fossil fuels, for example? Well, it's actually pretty easy, because what you can do, because of our economy and how important oil is, right, you can actually track the economic progression of crude oil, how much of it was bought, how much of it was consumed, how much depletes in the market over a period of time, and you can then assume that people buy crude oil for this purpose, to burn as fossil fuels for industry or for automobile usage or whatever. It's being used for that purpose. So if we can keep track of that in gallons or whatever, we can then use stoichiometry and use the equation that's involved with the burning of that fuel to figure out how much carbon dioxide would be produced if we burnt that much fuel. And that's a reasonable statistic. There's really no reason that you should argue with the possibility of that not being true. I mean, that doesn't account for everything, and it's certainly not is not a perfect set of data, but you could see where it could be pretty accurate. Okay, so if we know this to be true, for example, methane, natural gas, octane, which is the main component of crude oil, the gasoline that we would refined petroleum that we would burn in our cars. We know these reactions when you burn it with oxygen. And you know the products. Here's the balanced equations for this. If you could figure out how many grams, for example, of octane were purchased and thus probably used for engines, automobile engines or tractor engines or whatever. Same thing, you're still producing CO2. If you could come up with a number based upon the economy, how much of this was bought, you could turn that into grams, right? You could turn the grams into, guess what? What do we turn everything into? Moles. Once you know moles, you know that for every 2 moles of this that is reacted, 16 moles of this form, right? So what you could do is use this stoichiometry to predict how much carbon dioxide would form from the consumption of that much gasoline, for example. So that's how you get this kind of data. Okay, people don't just make it up. They don't, just pull it out of nowhere. So let's take a look at this. Now this is a basic definition, but let's illustrate something. We've already established well that I don't cook very well, but take this. This is an ingredient, so let's say, there could be other things, but let's say the basic. Just use this. Go with me here. Don't argue with me. Let's say these are the ingredients to make pancakes. All right? We've got, see, now stop. I've got flour, eggs, baking powder, and voila, pancakes. Okay? Now, that's it. That's all you need. Just crack it, put it all together, fry it, and eat it, and shut up. Okay. Come on. I'm trying to illustrate the point here. All right. Now, let me ask you this. Say this was the ingredients to make your pancake. You would need 1 cup, 2 eggs, half a teaspoon, and you could get 5 pancakes from that. Now, if you had 4 eggs, could you make 5 pancakes? Some say no, some say yes. First, I could say both is right, okay, but first with the no. Why could you not? Why would 4 eggs not necessarily give you 5 pancakes? No, stop. You're not seeing my point here. Well, okay, wait. What?
You wouldn't have enough of the other 2 combined. It would not balance.
There you go. See what she's saying. Now, I know some of you could say yes because, I'll just make the pancake smaller. Okay, whatever. Or bigger or whatever. I don't. It don't matter. I'm getting mad now. I'm about tired of this already. Now just go with it. My point is, if I have 4 eggs, big deal. Because I still don't have enough flour. I would need another cup of flour and another half a teaspoon of baking powder in order to make 10 pancakes, let's say. I would have enough eggs to make 10 pancakes, but I wouldn't have enough of the other stuff to make 10 pancakes, right? So what would limit this reaction, to use the chemical terms, what would control how many pancakes I produce would then be either how much of this I had, right, or how much of this I had. And whichever one of these was the smallest number of what I had, that would be the one that determines everything, how many pancakes I could make. Okay, that's an easy way. We can apply that to chemistry in terms of reactants and products in the same situation. It doesn't matter. There's a ratio. In this case, it's a 1 to 2 to 1/2 ratio of the things needed to make these 5 pancakes. In chemistry, it may be a 1 to 2 to 3 ratio to produce a certain amount of product. But what you got to realize is, you got to look and see which reactants are available and how much of them that you have to see which one's going to run out first. Okay, which one is going to limit the amount that you can get over here. And I'll show you what I mean with some equations here in a minute. But we can use this as conversion factors. Okay, the 1, the 2, the 1/2, the 5. Realize these are equivalencies. We could say that 1 cup of flour would have to be equivalent to 2 eggs, or we could say that 1 cup of flour is equivalent to a half a teaspoon of baking powder. We could say 5 pancakes is equivalent to 2 eggs. You could write this a whole bunch of different ways, as long as our equation is correct. So you can see the importance of balancing the equation. So I can pull any conversion factors I want from what you see right here. Okay? All right, so if you want to make more or less than 5 pancakes, you use the number of eggs you have to determine the number of pancakes you can make. Okay? Let's say you just do that. Okay? Assuming you have enough flour and baking powder. That's a big assumption. What you are assuming is if I'm going to use my eggs to determine how many pancakes I want to make, you've got to be sure that you've got surplus of all the other ingredients, and that's not going to be an issue. Okay? So if I used 8 eggs, how many pancakes could I make? Well, you could do it in your head. You know that there was 2 up there for 5, so you multiply that by 4. 5 times 4 is 20, whatever. But realize, in real life, you're going to be dealing with numbers in chemistry that are not going to lend themselves to that easy of math. You want to set it up with a conversion factor. You know that according to this, on the previous page, we said that we could say there was an equivalency between 2 eggs and 5 pancakes, right? So if I have 8 eggs, how many pancakes can I make? Well, I can make 5 pancakes for every 2 eggs. That would leave me with 20 pancakes. Okay? Easy enough. So, the balanced equation, what this tells you is similar to the recipe that we just saw. When you have a balanced equation, what you have is a recipe for the number of moles of each thing present. Okay? It can either be the number of actual atoms or the number of moles, because all the moles are is a number, the same number multiplied by all the number of atoms anyways, right? So you could use the equation to represent either actual atoms and actual molecules or moles of atoms and molecules, either one. Okay? So if you have this, nitrogen reacting with hydrogen to give you ammonia gas, it tells us that there are 3 molecules of hydrogen, 3 H2s, that react with 1 molecule of N2 to give us 2 molecules of ammonia gas. Another way to look at this is, let's multiply everything you see there by 6.022 times 10 to the 23rd. If you do that, now you have moles, right? So you could say 3 moles of hydrogen gas react with 1 mole of nitrogen to give you 2 mole of ammonia gas. So you could look at it in either terms of atoms and molecules or moles. It's the same thing. Okay? Okay, now that gives us a conversion factor. So if we know, for example, how much nitrogen we're starting with, we could predict how much of this would form based upon that amount of nitrogen. Okay? Let's look at an example. Sodium chloride forms by the reaction that you see down here between sodium and chlorine. We'll say it's elemental. We'll say it's solid sodium reacting with gaseous chlorine. It's going to give you solid sodium chloride when that happens. All right. I want to know how many moles of NaCl result. How many of moles will form from the complete reaction of 3.4 moles of chlorine. Okay, assuming there's more than enough Na. What that tells you is this is not an issue. You've got a whole big container full, however much of this you need. What is going to limit you, thus it says the complete reaction of, that means all of this is going to react, and 3.4 mole of it is going to react. If all of this reacts, how much of this can form from that? Okay, here's all you need to know. You need to know what is the ratio, what is the recipe comparison between Cl2 and NaCl. It's 1 to 2, right? So that means we can answer this question. That's all we need to know. So we set it up. I'm given 3.4 moles of chlorine. I want to know if I have that much chlorine, and this is my recipe, how much salt can form from that much chlorine. And I know this. Whoops, go back one. I know this, according to my equation, it's a 1 to 2 ratio. I know that for every 1 mole of chlorine that's present, I can form up to 2 moles of sodium chloride. All right, so I'm going to go from moles to chlorine to moles of sodium chloride. And the way that I'm going to do that is I'm going to use what? Anybody know? Stoichiometry. Okay? We're going to use stoichiometry. We're going to use the numbers, the coefficients that are in this chemical equation up here to do that, because those can represent mole values. So what I will say is, if I'm going from moles of chlorine to moles of sodium chloride, according to my reaction, I know that there's 1 of those for every 2 of those. In other words, 1 mole there for every 2 moles of that will form. That means I can write that down here. Put down 1 mole of chlorine down here, 2 moles of NaCl up here. I can get to moles of NaCl and I'm done. That's the answer to my question. Okay? Just keep in mind where you're starting and where you're going to. You should be able to keep this map straight in your head. Realize where these numbers come from. They come from the coefficients, because that tells me how many of each things I have. Okay? Not the little numbers. The little numbers tell me how many atoms are stuck together to make that molecule. It doesn't tell me how many of those molecules are present. Okay? Only the big numbers. All right, so I take my 3.4 moles of chlorine. I multiply by my stoichiometric ratio for the equation 2 moles of NaCl, 1 mole of chlorine. Bingo, I get moles of NaCl. In this case, 6.8. 6.8 moles. Okay? Which makes sense. Just use some common sense without any math. You can see that, obviously, however much of this I use, twice that amount is what's going to form in terms of NaCl, right? I'm going to have twice as much NaCl as what would have reacted in terms of moles over here. If I have 3.4, what's twice of 3.4? 6.8, right? So this makes sense. It makes logical sense that this would be the case. Sig figs. I believe this was 6.8. Okay. Questions about that? Yes? Yeah, it's just an equivalent because we can't say that 2 eggs are equal to 5 pancakes. But what we can say is we can use those to create a ratio. We're not saying they're equal, but we're going to say they're equivalent because in the process. Yeah. Okay, now that we can grasp that, realize that in the real world we don't take mole measurements, right? We don't have any instrumentation to do that. What can we measure? Mass, grams, right? And then if we have grams, we can then obviously do a math step and convert it into moles. That's what you're going to have to do. Okay? So, mass to mass conversions, it's the same thing, except we're going to add a step to go from moles to grams. All right. You already know this. To go from grams to moles, we've got to use the molar mass, right? That's on the periodic table. You can look that up. Don't worry about all that. It makes it too confusing. Let's take a look at this problem and see what I mean. It says in photosynthesis, ooh, general biology, right? In photosynthesis, makes me think of, what is it? Is it Billy Madison? He goes back to school. Chlorophyll. It's more like borophyll. In photosynthesis, plants convert carbon dioxide and water into glucose. Here's your formula for glucose. So you know that you're taking in carbon dioxide, and you know you're reacting it with water, and one of the products you're getting is glucose. Okay? According to this reaction down here. I want to know, not moles this time, I want to know grams, because that means more to me. How many grams of glucose can be synthesized if you have 58.5 grams of CO2? In other words, if I had a room and I measured out 58.5 grams of CO2, say it was dry ice or something, I measured it out and I let it vaporize in this room, and I know exactly how many grams are in here, and I've got plants in here, and the only thing they were given was 58.5 grams of CO2, I want to know how much how much sugar that will make from that 58.5 grams of CO2. That's a valid question, right? Otherwise, you have to let the plant grow and extract every little thing from itself. Not possible. This is really, only through stoichiometry is it even possible to come up with a theoretical answer to a question like this. Okay, so assume that there's more than enough water to react with all the CO2, just like in biological systems, right? There's tons of water. It's never going to be a limiting factor. So let's say there's tons of this. You've got a certain amount of this, and if you know how much of this you have, I want to know how much of this forms. Now, I could also ask you how much oxygen forms. That would be good, too, because then you could see how much oxygen forms from these plants that we can then consume. And you could certainly answer that question, but I'm not asking that. I want to know how much sugar forms. Okay? Now, what am I going to have to do to this gram value, then, in order to use this equation? I'm going to have to change it to moles. You need to understand something very clearly. You can never, ever, ever use gram values in stoichiometry. You cannot use gram values to compare things in terms of recipe. Why? Because everything weighs different, right? The only thing that is consistent, a mole is a mole no matter what it is you have. So you've got to use moles so that you're comparing apples with apples. Okay? You can't just use grams. So do not try to use grams and say 6 grams of that gives you 1 gram of that. Wrong. 6 moles of that will give you 1 mole of that. Then you'll have to convert that into grams because these things weigh differently. So you cannot use grams. Okay, so I would use, anytime you're using a chemical equation, always, you're dealing with moles. So get there. Okay? 58.5 grams of CO2, convert it to moles. And I would use what to convert it to moles? Molar mass. How would I get the molar mass for CO2? Is CO2 on the periodic table?
Well, you have to add them together.
That's right. I would take a carbon and 2 oxygens, add them together. I would have the molar mass. That would be in grams of how much 1 mole of that would weigh. I could create a conversion factor and say 1 mole of CO2 would be equal to however many grams that added up to be. Then I could use that to convert this value into moles. Okay? All right. So here's where I'm starting, 58.5 grams. I want to know grams of sugar, of glucose. You're going to need to know, ultimately, since what will happen is when I go from grams of carbon dioxide, I'm going to turn that into moles of carbon dioxide, right? And then when I get an answer, guess what my answer is going to be in for glucose? Moles. But I want the answer in grams. So then you're going to have to convert moles to grams in terms of glucose. So that means you're going to need, and you don't have to write this down now, you'll figure it out when you're doing the problem. But one thing that you're going to end up needing is the molar mass of glucose, which is figured in right here. Okay. What does it say? Oh, yeah. Sorry. No, nothing happened. No, I didn't take anything away. Nope, it's supposed to be 58.5. All right, and you're also going to need the molar mass of CO2, which, like you said, you can look up on the table. Okay, but I went ahead and wrote them down here. Okay, so what we know then, if you know the molar mass is 44.01 grams for carbon dioxide, we know that 1 mole of CO2 would thus weigh 44.01 grams if we had a mole of it. Same thing with sugar. 1 mole of it would weigh 180.2 grams. Okay, so we've got our arsenal built now. We know what all we can use to tackle this problem. We also know from stoichiometry that, according to our equation up here, you're going to need, for every 1 mole of glucose that forms, there's going to be 6 mole of carbon dioxide having to be put into it in order for that to happen. That's where this equivalency came in down here, okay, from the chemical equation. Okay. You're going from, you tell me without looking, we're going from grams of carbon dioxide to what? Moles of carbon dioxide. Moles of carbon dioxide to moles of glucose. Moles of glucose to grams of glucose. Good. Now we can fill in how we're going to get there. We're going to go, what is this? This is the molar mass of carbon dioxide. Good. So we go from grams to moles of CO2. We use the molar mass, okay, as a conversion factor. Now when we got there, we'd have an answer if we stopped there in moles of CO2. We don't want to stop there. We want to keep going. So to go from moles, because this would cancel out, right? Grams of CO2, grams of CO2. We're at moles. How do we go from moles of CO2 to moles of sugar? We use our equation. We use stoichiometry. We know that for every 1 mole of sugar that forms, 6 mole of CO2 is required to react with it. Okay, so we put that there. We can cancel out moles of CO2. Now we're left with moles of sugar. Are we done? No, we need grams. What do we need in order to go from moles of sugar to grams of sugar? The molar mass of sugar. So if we had 1 mole of it, it would weigh this much. Now when we cancel out, we get a final answer in grams of glucose. Okay? And there's the numbers plugged in. All strung out. Don't do it in your head anymore. Okay. There's your raw number. Adapt, change it to meet sig fig requirements, 39.9 grams. So with an input of 58.5 grams of CO2, you should be able to theoretically withdraw, if it was a perfect world, almost 40 grams of sugar from that. Pretty interesting. At least I think so. I could be standing alone on this issue. All right. All right. Let's go back to our pancakes. Tell you what, people. You got guts, I'll give you that. All right, now here's what we know to be absolute truth. I've decided so. Now, how would this change if you didn't have an endless supply of whatever it is you need, and you go to your pantry / refrigerator / floor / wherever it is you keep this stuff, and you find out that you only have a certain amount of each thing, and you got to figure out how that plays into your recipe. Okay? Say you have 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder. How many pancakes could you make now, assuming that you had to follow this recipe? Okay. You see how that logic, see how that worked? Okay. I'll show you. Let's look it up. Here's what I want you to do, though. For pancakes, that's one thing. For chemical reactions, a little more difficult, right? So what I want you to do is approach this problem using each thing that you see here, each ingredient. Okay, so for example, what I want you to do is, which is what you did in your head, you just don't realize it. what I want you to do is take your 3 cups of flour, figure out how many pancakes that could make. Then take your 10 eggs and figure out how many pancakes that would make. Then take your 4 teaspoons of baking powder and do the same, and guess what? Whichever one of those produced the fewer amount of pancakes, obviously is going to be your limiting factor here, right? Do you see what I mean? Because if you had 3 cups of flour, you could make 15 pancakes. If you had 10 eggs, you could make, 25 pancakes? If you had 4 teaspoons of bacon, too much. But you see the point. And then whatever one of those produces the fewest amount of pancakes, then that's what's going to control how many pancakes you can make. So let's set this up in math form using conversion factors to do the same thing. 3 cups of flour. You know that there's 5 pancakes for every 1 cup of flour. So there you go. There's your math to show 15 pancakes. 10 eggs. You know that for every 5 pancakes requires 2 eggs. So you get 25 pancakes. 4 teaspoons of baking powder. You know that for every 5 pancakes you need a half. So you can make 40 pancakes. But given that this is all you have, obviously you're not going to be able to make 40 or even 25 pancakes. You're going to be limited to only making 15 pancakes. Now keep that same application in mind as we go into chemical reactions. Now, like I said, each ingredient could make a different amount. We have to compare those since everything has to work together. So in this case, we can only make 15. We would call then the flour in this case, to give it a chemical term, we would call the flour the limiting reactant. The reactant that limits how much product you're going to get. Okay, so know that term, limiting reactant. You may also see it listed as limiting reagent. A reagent and a reactant mean the same thing. Okay. Now, something else I want to point out. The maximum number of pancakes that we make depends on that ingredient, like I said, but we call this whatever that maximum number is. Like, for example, with the flour, we could make up to 15 pancakes. If it was a perfect world, and we got every drop of pancake out of what it is we were trying to do, we would call this this is our theoretical yield. In theory, if it was a perfect world, we would be able to produce 15 pancakes. Okay? We could produce 15 pancakes. However, realize that if you're anything like me, chances are that, somehow something's going to get screwed up in this process. It could be that somebody's pancake falls on the floor. Now, you might be the person that throws that away. That just goes on the bottom of somebody else's stack if you're at my house, okay? So and realize that things could happen. You could break an egg. You could drop a pancake on the floor. Experimental accidents happen, okay? It's bound to happen, and as a result, you're never probably ever going to get your actual theoretical yield for any equation that you run. So what we can do is calculate what's called, or look at, actually, and measure what your actual yield is. And when you take your actual yield, let's say 14 pancakes is what you ended up with when this big fiasco was over. Say you ended up with 14 pancakes. How does that compare to your theoretical yield? Your actual yield was 14. Theoretically, you should have been able to produce 15. So what's called your percent yield? Your percent yield is how close you were to getting what it is you were supposed to get. So how do you think you would calculate without looking? How do you think you would calculate percent yield? Yep, your actual yield divided by your theoretical yield to turn that into a percentage, right? It's just like shooting free throws. How do you know you're a 70% free throw shooter? Because you shoot 10, if you hit 7 of them, 7 divided by 10 is 0.7. That's 70%, right? It's the same thing. Okay, so we can calculate what's called percent yield. You're right. You take the actual yield that you got, divide it by what you were supposed to get, turn it into a percent, and you've got your percent yield. All right. So if you had 11 pancakes by the time you were done, you're supposed to get 15, your percent yield is 73%. Dealing with pancakes, that's not too hot. Not too good. Dealing with chemistry, 73% might not be too bad. Just depends. Okay. The theoretical yield, keep in mind as we deal with reactions here, your theoretical yield of any chemical equation is going to be due to your limiting reactant. However much product your limiting reactant can form is going to determine your theoretical yield. Okay? All right. Let's take a look at this problem. If you have 11.5 grams of carbon, and you react 11.5 grams of carbon with 114.5 grams of, you tell me, what is this? Cu2O. How would I? Copper 2 oxide? What is it? It's copper 1 oxide. Why? Because what's the charge of oxygen always? -2. If I've got 2 coppers there to balance out a -2 charge, each one has to have a +1. So that's copper 1 oxide. All right. So I'm reacting 11.5 grams of carbon with 114.5 grams of copper 1 oxide. According to this reaction that you see, I form 87.4 grams of carbon. Okay, or sorry, of copper. My fault. So I'm mixing this much carbon, this much copper 1 oxide, and I can get, when I measure this and I collect my product and I weigh it, I get 87.4 grams of solid copper. All right, so here's my question to you. If this data is correct, and assuming that it is, I want to know which one of those was the limiting reactant. Then I want to know what was the theoretical yield and what was your percent yield. Okay? How do I find out? How do you think I'm going to tackle this problem? Now think about it. Don't give up. Don't throw your arms up. What I'm going to need to do in order to find out what my limiting reactant was is, first of all, figure out how much copper could form from each one of these, right? I got to look and see which one of these could form the least amount of copper. Whichever one of those could form the least amount of copper was going to be my limiting reactant. Then I've got to look and see, okay, I'll take my limiting reactant and see how much actual copper I could form from that and compare that to what I actually got. Okay, so stay with me. Here's what I know. 11.5 grams of carbon, to reiterate. Reacting with 114.5 grams of Cu2O up here. And I know that I collected this much copper. My question is, what is my limiting reactant in this case? What is my theoretical? What is my percent yield? Okay. All right, how am I going to do this? You're right, we've got to turn everything into moles before we start messing around with chemical equations. So the first thing you can do is just make yourself feel better and start doing some partial credit work here and turn everything into moles. So collect all your molar masses that you need. Okay. So here's a molar mass of copper 2 oxide. You're going to need that. You're going to need the molar mass of copper. You're going to need the molar mass of carbon. These are all going to allow you to go from grams to moles. Okay. And we also know that according to stoichiometry, it's a 1:1 to 2:1 ratio. So that means 1 mole of copper 1 oxide could give you 2 moles of copper, according to our reaction. Also, 1 mole of carbon could give you 2 moles of copper from the chemical equation. These are things that you could, if you don't write down at first, that's okay, because you'll see where you'll need them as you go along. Okay, here's what we need to do. You need to break this problem down. Anytime you have a limiting reactant problem, break it down and solve it separately for each reactant involved. Okay? Solve it for each separate reactant, like we did with the pancakes. You did it for flour, then you did it for eggs, then you did it for whatever the other one was, baking powder, or whatever. You had to solve it each time to compare how many pancakes each one of those would give you. It's the same principle. Instead of using flour and eggs, we're using copper 1 oxide and carbon. We've got to do the same thing, though. We've got to see how much product could be formed with the amount of carbon that we have, how much product could be formed with the amount of copper 1 oxide that we have, and then see how they compare. Okay? And it's just like the pancake thing. Whichever one's lower is going to determine how much is going to be the limiting reactant. Okay? Whichever one produces the least amount of product. Okay, so we're at grams of carbon. So notice we got 2 rows we're setting up here. 1 for carbon, 1 for Cu2O. Keep them separated. We're going to do the exact same steps for each one, though. You'll see what I mean. I'm going to have to go from grams to moles, right, for each one of those in order to use my chemical equation. I do that by using the molar masses for each one. So now I'm at moles of carbon, and I'm at moles of copper 1 oxide. Now, what I need to do is figure out, if I know how many moles of carbon I have, I've got to figure out, okay, how many, since I'm dealing with, my product here that I care about is copper, right? So I'm looking down here at copper. If I have this many moles of carbon, how many moles of copper could I have? So I would have 2 moles of copper for every 1 mole of carbon. Now, what I don't know is exactly whether it's 2 or not in terms of the actual number of moles. I do know that where the 2 comes from, yes, you're right. Every 1 mole of carbon that I have, there are 2 moles of copper present. That's right. But I don't know how many moles of carbon I have because I have to do the math. See what I mean? I've got to pull in my gram value down here, and it may not equal 1 mole. It may equal something else. But nonetheless, I can go from grams to moles. Okay? Then I can go from moles of carbon to moles of copper. How? Stoichiometry from the equation, the 1-to-2 ratio. Okay? Now, from moles of copper, what can I do? Change it to grams. Then I can compare both of these numbers. I do the same thing down here with Cu2O. Okay? I have stoichiometry here using these for this reactant. I use the molar mass here, which is going to be the same because it's still copper in both cases. And I can figure out how much of copper will form in grams. Now think about this. Before you shut down, before you decide that there's no way that you can understand this, I want you to look at the board, and I want you to stop for a second. I want you to reason through this process. Don't try to memorize steps. Don't try to memorize formula. It's not going to work. This isn't math class. Okay? What this is problem solving. It's using math to solve problems, and to solve a problem, you've got to know where you're starting and where you're going. You can't just put your head down and go and expect to solve a problem. It's not going to happen. Okay? There will be open-ended questions on this test where you have to solve these problems. I promise. So if you want to make it, you're going to have to think about it. Now look. Clear your mind for a second. Just clear it. Okay? Imagine that you get to go to where my wife's going here in a couple days, down to the tropical rainforests of Guatemala. It's nice. It's warm. Beaches, sipping Mai Tais, with a screaming kid hanging off one side of you. It's nice. Clear the mind. Waves splashing against the shore. Everything about it is better than where you're sitting right now. Okay? Just pretend like, kids weren't an issue and they never existed and all that kind of stuff. Just for a second. You can have them back when this is over. Okay? All right. Now, here's my situation. I've got a recipe that I'm trying to follow. I've got a certain amount of product that has formed. I've had a chemical reaction happen and something formed. And I collected that something and I weighed it and I got a certain amount of it, so I know how much is there. I know how much formed. I also know what I mixed together in order to get this product. I know not only what I mixed together to get this product, I know how much of each stuff I mixed together to get this product. Okay? All right. Now my question is, if I know that, if I know what it was that formed and how much of it formed, basically I know that, for example, pancakes formed, and I know how many of them formed, and I know that I used 26 eggs and, I don't know, a stick of butter, whatever. I don't know. That would be nasty pancakes. But say I use these 2 ingredients, okay? You know how much you dumped in there, and you know how much pancakes you ended up getting out of that. What you don't know is what's sort of left over in there that didn't react. Because all of it wouldn't have reacted. You have a certain ratio. You have a certain recipe that goes into the formation of these products. Whatever it is you put in here, whatever ingredient that you put in, one of those reacted completely. The other one did not. There's still some of it left over. If you can keep track of how much of each you put in there, and you know how much of the product formed, you can figure out which one of those disappeared and which one of those are still left over. Right? That's this problem. It's just with bigger words that you're not used to. And fancy symbols and all kinds of stuff. Yeah.
So is the limiting reactant always?
Yes. But now that you have the answer to that homework problem, it's important to understand why that is true. Okay? It has to be by definition. Okay? It has to be by definition. That's what the limiting, that's how it got its name. It's the one that limits the reactant and is completely consumed. Now, take all this that you see and think about it in your head. What's happening? You have a certain amount of carbon, one of the ingredients. You know how much you put in there. You have a certain amount of grams of copper 1 oxide that you put in there. and you know what happened as a result of mixing those two things together, you got a certain amount. You got this much copper, solid copper that formed. That was your product that formed. Now your task is to figure out which one of these two got used up, got completely consumed, versus which one is left over, still floating around in your chemical vessel, okay, your reaction vessel that you did this experiment in. Because one of those is still going to be there. The other one's not. You got to figure out what it is. All right, so I take however much carbon I had and however much copper 1 oxide I have and start going through the problem-solving process. Try to figure out, if I had this much carbon, how much of this could form. Sort of like, how many pancakes could I make if I only had this much of the ingredient? Okay, how do I do that? Well, I got to use this as my recipe, right? This is my recipe. But I cannot use this recipe until I have what unit that I'm working with? Moles. I cannot use my recipe until I have moles. So this first step that you see here in both of these cases is just taking our initial ingredients and converting them into moles so that we can then use our chemical equation. Okay? That's our first step. We did that for both of them. It's the same step. They're different numbers because each one of them weighs differently in terms of how many when you have a mole of it. So these numbers are obviously going to be different. Okay, now we have the moles. We know how much of each ingredient we have in terms of moles. Now, if we know how much of each ingredient that we have, how do we figure out how much of this forms? That's what we're dealing with here, copper. You have to set up a conversion factor. Like if I said there was 2 eggs gives you 5 pancakes kind of thing, I know that for every 1 mole of carbon that I have, it'll give me 2 mole of copper. That's what I know. Okay, I'm using my stoichiometry. I'm using my recipe now. So I have to position these in a way that the things cancel out the way I want them to. So I put 2 mole of copper on top. I put 1 mole of carbon on bottom. And what that tells me is how many moles of copper I could produce from the given amount of moles of carbon that I have. Okay? That's what this is saying. Now, why did I do this next step? I could have stopped here and I could have had an answer in moles. But if you look at the problem, everything's in grams. Okay? So that's why this last step is here, to take this mole value now and put it back into grams. So what you'll see in the midst of all this chaos that you see up here is there's only one really, really important step, right? One central step that's understanding the theory behind what you're doing, this right here. This is the stoichiometric step, using the equation. These are just conversions to get from grams to moles, and this one from moles to grams. That's all this first and last steps are. Okay? All right, now, when I do this, and I plug in this amount, and plug in the proper numbers, what you will see is one of these numbers will be smaller, a smaller gram value for copper than the other one. And guess what? Whichever one gives you the smallest gram value of copper, what that means is it's going to get all used up and only give you that much. The one that gives you the bigger one, that's what's going to be left over. Not all of it's going to get a chance to react. Does that make sense to you? You understand what I'm saying? Okay. So plug in the numbers. Notice the difference. With 11.5 grams of carbon, I am able to make 122 grams of copper. With 114.5 grams of copper 1 oxide, I'm able to make 101.7 grams of copper. So I ask you, what is my limiting reactant? Copper 1 oxide is my limiting reactant, right? So, what does that tell you? It tells me that if I ran this reaction, I should get how much copper forming? I should get 101.7 grams. Did I get 101.7 grams? What did I get? 87.4. My theoretical yield is 101.7 grams. My actual yield is 87.4. What next?
So the limiting factor is the copper and
Well,
the smaller number.
Whoa. Stop. My next step before is to find the percent yield. Okay? How do I calculate the percent yield for this reaction? So I take 87.4 divided by 101.7, get a percent. That's my percent yield. Okay? Now, was there any other comments? Yeah.
The 101.7 is the limiting factor and the theoretical.
No. The 101.7 is the theoretical yield. But what we did was we used the theoretical yield. here's the theoretical yield if we went off of carbon. Here's the theoretical yield if we went off of copper 1 oxide, right? This is how much copper would form in each of those cases. But this, since this number is lower, is the theoretical yield for this equation. Okay? This number is going to be reached first before that number will be. This is my theoretical yield. Huh? The limiting reactant, look, these two letters are different. This says copper 1 oxide. That says copper. The limiting reactant is the thing that reacts. This is the limiting reactant because it produces our lowest number, our theoretical yield. Okay? So this is our limiting reactant. This is our theoretical yield. Your limiting reactant produces your theoretical yield. Okay? Questions? Something to think about anyways, because you don't have anything else to think about as you're laying in bed tonight thinking, limiting reactants, how does it apply to my life? Pancakes. Yeah, exactly. So see, now what I have done for you, you're welcome, is ruined every possible IHOP experience from this point on in your life. You're going to be sitting there and you're going to be asking, how many eggs did you put in this pancake? And what was your limiting reactant when you were preparing my order? All right. All right, now, let me keep going. We got a few minutes here. How many slides do I got left? Oh, okay. Well, I'm going to be able to finish this. So let's stay. We're still on for the test. Yes, I'm excited. Okay. Oh, quit whining. Here we go. When 11 and a half, already here, sorry. We already did this. This is explaining what it is we just said. I just showed you on the previous slide. This is your least amount that formed, right? So this is going to be our theoretical yield. Whatever reactant went into forming that, which would be this, that is your limiting reactant. Okay? So there we go. To find your percent yield, you would take your actual yield divided by your theoretical. Your actual was 87.4. Your theoretical was, 101.7? You got an 85.9% yield. Not too bad. Pretty good. Okay? So there will be your full answer to that question. Notice how, think about it though. Think about, we got a couple minutes here, so I want you to think about how much you had to have learned already to even understand this problem. So that should make you feel good. Okay? The fact that you can follow me through this problem, if I would have thrown this problem up the first day of class, there's no way. Right? It's not even possible. But I could ask you this one question, and really it incorporates your ability to understand everything that we've done. You've got to know how to write things. You've got to know how things are named. You've got to know how to balance equations. You've got to understand charges so you can write, when CA and CL comes together, you've got to know how to write that in order to get the equation right. You've got to understand the math of conversion factors and how all of that works. You've got to know the elements. You've got to know the periodic table. You've got to know the charges that things form. You've got to know how to use the numbers on that periodic table. This is all stuff that you've already learned in this short amount of time, even to be able to approach this question. So, there you go.